Hi, I'm Tyson Cadenhead, and today we're going to be looking at microservices in a GraphQL world. There's a lot of really cool things you can do with microservices and GraphQL together, and that's kind of been the world I've lived in, so I think there should be some really interesting things to look at today. So what we're going to look at is we're going to learn how to build, scale, and decouple software and software teams to reduce the friction and push out more valuable features. I think the interesting thing to note here is that this isn't just a problem of technology. It's a problem of teams and being able to keep teams smaller and more decoupled from each other in order to push out more software. So what we're going to go over today, we're going to go over the monolith, basically how a lot of applications will start, and then how we migrate that to using microservices. From there, we're going to look at how you can use microservices together to create GraphQL APIs, and then we're going to look at how we would actually federate those schemas so that they can be used in a single endpoint. Then we're going to look at event-driven architecture and how we can pass events around without tight coupling between the services. Then we're going to look at micro-frontends, which basically applies a lot of these same concepts to the front end as well as the back end. And then finally, we're going to talk a little bit about how we can organize our repositories and kind of bring this all together. So before we get started, a little bit about me. My name is Tyson Cadenhead. I am a senior full stack architect at VHT, which is having a name change to Mindful. So pretty soon my LinkedIn will be updated, but right now it's VHT. Before working at VHT, I was the VP of engineering at Evolution Virtual, and before that, I was a CTO at Olympia. So I've had a little bit of experience leading teams and kind of going through a lot of this kind of architecture as well. I'm also the author of the Socket.io cookbook, and I'm just basically an enthusiast for serverless, GraphQL, TypeScript, React, and functional programming. I have a blog at venable.io, so I'll be probably posting more about this topic in the near future as well. So let's move right into the actual meat of this. So chapter 1 is the monolith. This is Jack. Jack had a great idea. He wanted to create a new product company called Widgets Incorporated. And the great thing was that Jack could figure out how to do some basic programming by himself, so he was able to start his own company. And the way he built this, he built a very simple monolith. He had a front end and an API. They all lived in the same repository, and they all got deployed together. And this worked really great for Jack because it's exactly what he needed, and it showed that his product could work. The problem is, as soon as he started getting customers, he realized that he couldn't do everything, and so he had to hire some more developers. So he hired a team. And the team immediately, once he started getting 7 or 8 developers on his team, he ran into scaling problems. One of his developers said, "I wish we could deploy the front end and the back end independently." The thing is that the deployment would take a long time, and sometimes you would just have a little change, like if you needed to move something on the front end from one side of the screen to the other, the entire application had to be redeployed. Which took a lot of time, and it could even cause downtime if they didn't do any kind of red-green deployment strategies. Another developer said, "This code base is large and complex." So Steve was always complaining, but they dealt with him and they got around that. So what they decided to do is to split up their teams by technology. So they had a front-end team, and they also had an API team. And each team had their own repository, so they could deploy independently. They could deploy their front end code independently of their API code. And this worked for a little while until they had to hire some more developers, and all of a sudden they ran into scaling problems again because they had a huge front end team and a huge API team, and so any kinds of changes that happened would be really intensive on both sides. They had a lot of trouble managing the deployments across the board, and then they just ran into a lot of merge conflicts. Steve came in and complained again, and he said, this code base is large and complex. So what are they going to do? So that moves us to chapter 2, which is microservices. So what they decided to do is they were going to create some RESTful microservices. And basically what they were going to do is let the front end know that there were multiple services that it could talk to. So if it needed products, it would call the product microservice and use basic HTTP verbs like get, post, put, and delete to manage the products. Same thing for users, payments, integrations, and reporting. And so they had smaller teams that managed each one of those microservices, and the front end knew all about it. There were some problems though. For one thing, they had to make too many requests. So for example, if you needed a product and you needed all the users who had bought that product, and then you wanted all their payments, you would have 3 nested requests that could be even more depending on what kinds of parameters you're passing into it. And so that was definitely a real problem because they were making way too many requests, which was slowing down the front end application. Another developer says we're fetching too much, and that's true because so for example, if you just needed the product and the product ID and name to show on the screen, they were actually getting back the entire product object, which could be all kinds of data that they didn't even need and weren't using, but they had to get because it was part of the API. Another thing to note is a lot of times with RESTful APIs, a pattern that people will use is they'll start adding common related models to a model. So like if the product had a list of SKUs that went with it, instead of making a SKUs like a SKUs request, they would just nest that under the product in order to make it easy to access for certain requests. The problem is that sometimes requests didn't need the SKUs for the product, so they were getting that back even though they didn't need it. The alternative to that is to keep their RESTful API very flat, but the problem with that is that a lot of times you have to make multiple requests, back to Tori's point. Another of their developers said there's no way to guarantee the types on the front end, which is true also because whenever the front end makes a request, there's no way to know for sure that the data that's coming back from the API is the type that we're expecting. So if we have a product with a price on it, it might come back as an integer, it might come back as a string. The front end just doesn't know for sure. And obviously, we can add validation on the front end to make sure that it's what we expect it to be, but that's a lot of logic that lives on the front end just for validating the request. And then we have another developer, Rich, who of course is on the payments API because his name is Rich, and he says, I'm scared of deprecating any APIs because anytime that anything changes, they would have to make sure that the front end, all the front ends that were talking to any API weren't actually using whatever part of the API that they were hoping to deprecate, which is very hard to manage. So that moves them to chapter 3, which was GraphQL. So here we have GraphQL microservices, question mark. So the idea here is that every one of their microservices that they had before, instead of being RESTful, they turned those into GraphQL schemas. And there's a lot of real advantages to even this approach because at this point you're actually every single schema gives you the types that you're expecting from the schema. So the front end knows what type of price is going to be coming back from the product because it's being revealed in the schema when the request is made. It also solves the overfetching and underfetching problem because, for example, here's a sample GraphQL query. So this is where we're getting a product. We're getting the ID and name of the product and passing in an ID. And so that will return basically a JSON object in the same shape as the request we're making. So here we get back get product, and it gives us the ID and the name, which are the two fields we requested. If we change that query to just be name, we would just get back the name, and not the ID. So it's only giving you back exactly what you asked for instead of giving you back things you don't want, or giving you back less than you actually need. The way that this works is something called the Schema Definition Language, or SDL, where we basically on the back end will define a schema that tells us what type everything is and that can be returned from the API. So here we're defining a type called a product, and it has an ID, and the exclamation mark after the ID means that it's required. So it'll actually throw an error if it doesn't come back with an ID. And then we have the name, which is a string. And then we have two different kinds of queries that can return a product. So we have the get product, which takes an ID argument, and then returns a single product. And then we have list products, which will return an array of products. You can see with the bracket notation that it's going to be an array. And then we have something called a resolver behind it that actually, based on the schema definition language, it will resolve whatever the data is that is requested. So here I just made up some kind of fake database queries, but basically if we called list product, we just do database.product.query and get back all the products. And so you can use this to basically resolve all the different queries. And the nice thing about this is it's just a function. So it's like whatever kind of data you need back, you're just getting back a pure function, and then you can do whatever kinds of things you need to do inside of the function, and then basically return at the end whatever you're expecting to come back from the schema. And then this is all kind of glued together with the schema, which is basically takes those type definitions that we showed before and the resolvers, and it makes an executable schema, which then you can pass into your server. A very popular server that most people use these days is Apollo server. There's other options out there, but it works really well for this kind of thing. After that's all present, all you have to do is make a post request to the server, and basically define what your query is that you're requesting. Which a query can be, you can have a query which is just basically what you would have as a GET request in a RESTful API, or you can do a mutation, which is basically what you would do as a put, a post, or a delete if you were using a RESTful API. So any kind of changes you're making to the model. And then you also have subscriptions, which are more for like real-time stuff, which we'll talk about here in a little bit. So this is working really well. They have all their GraphQL schema set up, and they have all of their different services using GraphQL. But the question is, where does the routing happen? The routing happens on the front end. The front end has to know about every single one of those GraphQL schemas and where they're located, and what the URL is to hit them. So they basically have client-side routing. This is an example of how that would work. You can actually, when you're making a request, if you're using Apollo Client, which is another GraphQL client, you can actually set context on the operations you're making. And so if I'm making a query, I could say that the context has a client in it, and the client is user, and if it's a user, then we would actually use a different URL that we're requesting whenever we make the request. And so you can split that up, and it gets pretty complicated and complex, especially for something that's being managed on the client side. So it's not necessarily ideal. Another issue that we have, because the routing is all happening on the client side here, is that we're still making too many requests. Because the thing is, if we need a product and users and payments all on the same page, we have to make requests to each one of those APIs individually. We can't actually get back all those things at once. So that leads us to chapter 4, which is federated schemas. And before we talk about federated schemas, let's talk about another approach we could have, which is to have basically a GraphQL API gateway sitting between your microservices and the front end. So this would be like a server-side gateway that has the schema definition on the API gateway, and then it makes a request to all the REST resources that it needs to resolve a request, and then gives it back to the front end. So it's basically treating those REST resources as like a database that it's going through to get back the data, and then it just returns it to the front end. One issue with that is there's no type guarantees between the REST services and the API gateway. We do know from the GraphQL schema to the front end what the type is going to be, but there's no way to guarantee that if the schema is requesting users, that the user's name is going to be a string, because the REST resource doesn't have typing on it. Another thing is, Steve says, why do I have to own all the schemas? There goes Steve again, always complaining. But I mean, it is a valid question. Like, why does he have to be the owner of this this schema that lives right in the middle of everything, that is very arduously defined by the REST resources underneath it? Well, we're tired of Steve complaining, so Steve is fired. All right. So now we have another way we can do this, and that's with a federated gateway. And this may look a little bit similar to the original one that I showed a minute ago, but the difference here is that the schemas get with a GraphQL federation get defined on the services themselves. So product has its own product schema, users has a user schema, and they all get fed into this one central federated service that basically does query planning whenever you make a request. It grabs all of the schemas that are available, and then it resolves based on what is being requested. So the way this works, here we have this is the federated API that sits at the top of the other services, and it has an array of subgraphs. And the subgraph it has URLs for each one of the graphs that it can be resolved. So if we had the product graph and a user's graph, they would both be separate URLs. They would get passed into this super graph SDL object, and at that point they would be basically one thing that could be executed by themselves. And then the other thing to note is that for each one of the schemas that is being exposed, you have to expose it as a subgraph schema. So we could pull in Apollo subgraph, and that exposes it as a subgraph schema, which makes the other schemas be able the federated schema be able to grab that subgraph and know about its type definitions and resolve it together with the other ones. Another thing to note is you can actually extend the types whenever you're using subgraph schemas and federation. So here on the product service, let's say we have a product type which has an ID and a name. What we would do if we wanted other services to be able to use the product type and build off of it is we would add something called an entity. And an entity is basically defined by doing this @ key and passing in a field, which is going to be your identifying field, which usually would be your ID if you have one. And that will basically say that this is the key that you can use to know that it's the same thing as what we're requesting. From that point, in the user service, so before we were in the product service, now we're in the user service, we could actually extend the type of product. So you see there before product it says extend type, and that will actually make it so that it knows that it's pulling the type from somewhere else. We also need to mark the @ key fields like we did before, and then we mark the ID that we're pulling in as external because it's not coming from this service. It's coming from the product service. But let's say we wanted to add the author of the product, so the person who created it. What we would do, we just add that onto the extended type. So we do creator and pass a user on there. And this is available on the user service, so we can actually resolve it in the user service, not on the product service. So we're still keeping our services decoupled, but we're able to extend types off of other services. The next thing to talk about is event-driven architecture. So at this point, we have basically our whole structure of how the API can flow from the top to the bottom, federated services in between. But now, like, what do you do if you want to be able to pass events around? So let's say you create a new user. The user would, we somehow want to show reports on what users have joined, how many users have joined the system in a certain amount of time. The way to do that is whenever actions happen on your APIs, you would flow the events into some kind of event router. There's a lot of different kinds of event routers that you could use. I'm not making any suggestions at this point, but basically you need some kind of pub sub mechanism that takes in your events and publishes out that the event has happened, and then any service that wants to use that event is going to say, oh, I need that event, and so we have this user created event going into the event router. Reporting is listening for user created. When it happens, it adds a record to the reporting database. Another really cool thing about having this whole event router flow is that GraphQL subscriptions are not currently available on federated APIs. So we really need some kind of subscription service. And remember, subscriptions are for like real-time stuff. So like it's basically like the GraphQL answer to WebSockets or MQTT or some kind of real-time service that can update your front-end code. So what we're going to do is we're going to add a subscription service off of the event router. So anytime that an event comes in that we're listening for on the subscription service, we'll just respond to that topic by triggering whatever event is being subscribed to. So basically, it flows like this. It goes from the front end. We have some kind of, like a user is deleted. It goes through the gateway to the users, and then once that's saved, we'll pass that event on to the event router, and the subscriptions will be listening for on user deleted, and then it will just trigger that function up to the front end. All right. Next thing is this is a subscription, like a basic way that we would subscribe to something. So we just have this on user change, passing in an ID, and then we have take the whatever arguments we want back from it. And then whenever this happens, it'll just it'll trigger on the front end, and we'll have that update. So I'm going to show a couple of basic recommendations of how you could go about implementing this structure, because it's really not it's not stuck on a certain kind of technology. There's multiple ways to implement this, but this flow itself I feel like is really powerful. So one way you can do it is have a front end with something like an Angular or a Vue going through multiple microservices. So we could say that each one of these microservices underneath this, like the gateway, the products, everything, is a Docker image running Node.js, and so whenever those are called, they could be even separate EC2 instances, even running in separate accounts, and so they each go through there, and then we have something like a RabbitMQ sitting as our event router. So when events come in, RabbitMQ gets triggered, and then it can trigger stuff back up through the subscriptions. So that's one way to do it. Also here I'm using a Postgres as an example of a database. So whenever something gets added to the Postgres database, that's when the data flows into the event router. Another cool way you could do this is more of a serverless approach, which is kind of more of the world I live in most of the time, is a front end like something like a React or something like that. And then each one of these microservices is basically an API gateway with a Lambda, and so that goes through the API gateway, and then saves off into the DynamoDB database. The cool thing about DynamoDB is it has streams as a feature that you can use on it. And with streams, you can actually, when data happens, it'll actually stream that data out, so you can trigger another event. So we could actually just pass this on to a queue or just straight onto a event bridge, which would be our event router. And then once that gets triggered, it could fire off the subscriptions Lambda service, which would update the front end. So with all that in place, let's talk a little bit about micro-frontends. So basically at this point we had all of our backend kind of segregated in the way we want it to be, but we also would really like to be able to have our teams be able to have control over the front end of the part that they're working with as well. So like the product team should also be able to work on the product front end. So one way to do that would be to split this up kind of in the same way, to have products and users and payments and integrations reporting on front end as well. So if you look at a page, the thing is you rarely have everything working on in the same page. Like you're not just going to have a profile page and a product page and a payments page. You're going to have them all kind of on the same screen a lot of times. And so in this example, we have, products and user payments are on the user screen. And the way that we could split this up is we could actually have modules that are exposed through Webpack when we're building it on the front end. So here we're basically requiring the federated plugin, and then we are exposing a file by the name of payments.js and taking in the federated module. So whenever this builds, it's actually going to have an exposed module called payments.js that gives us anything that we provide on that module. And then on the place where we're consuming it, we actually define these remotes, and these will be like all the different services that we're consuming through module federation. And so here we're consuming the payments and we're consuming products, and we basically just give it a URL where to find the thing, and then from that point it basically is treated like any other import that you would use in a project. So we're just importing the payments. Here it's a React component, but it wouldn't necessarily need to be. It could be anything you would export from JavaScript. You would just basically use it in the same way. So all of that said, let's move on to how we would actually organize our repository. So the thing is, at this point, we have full stack teams. We can, the product team can control both the front end and the back end. But how are we going to organize how our code is, where it's stored and how it runs in CI? So Steve comes back and he says, "But how do we deploy it?" Wait a second, didn't we fire Steve? So we'll slap a restraining order on Steve because he doesn't need to be hanging around our office and annoying us all the time. Alright, now that he's out of the way, one way we could do this is we could actually have multiple repos. So we'd have a repo basically for every service, and every front-end service, every back-end service, and even like we might have some component library, back-end common, just a bunch of repos that all kind of get stitched together. But one issue with the multi-repos is that your PRs are going to cross across multiple repos frequently, particularly if you have people working on the front end and back end. They're going to be making changes that you won't be able to merge in your front end until the back end code is merged first, and it creates a lot of dependencies in your PRs. So one approach to that is to have a mono repo where you basically have all of your services all sitting in one repository, and they all get deployed together, and they all basically live together. There's some good sides and bad sides of that. So one thing is that the deployments can be slower, because if you're deploying everything, then you're going to run into issues with like the entire thing is going to be held up by the slowest part of your stack, even if you start splitting up based on what the packages are. Another thing is that if you do try to start basically only deploying the things that have changed since the last time you pushed, you're going to have more complex CI/CD because there's just a lot of complexity there. Just basically checking on what's changed and then trying to respond to whether it's actually deployed last time or if it's failed. You're basically going to be, in some way, you're going to be hand spinning a pretty complex system to be able to handle that. The other thing, which could be a pro or could be a con, is that everybody's going to be in the same repo. So because everyone's in the same repo, you basically are going to have a lot of pull requests. They may be going on top of each other a little bit, but the good part about that is that people will be able to cross like if a change in product does affect something in the event router or even in another service, they could all flow together, and the PRs are very clean because they're exactly what they need to be for that feature across the stack. Another approach you could take is multiple monorepos. And in this approach, you basically have each one of your products is its own, or services is its own repo, front end and back end, and those deploy together, and then you'll have some kind of off to the side packages that you'll probably have for like shared components and back end components and libraries, and then you're gonna have like these like platform kinds of components that don't necessarily fit into anything else, like the event router, your front end clients, your gateway API and subscriptions API. All that stuff kind of like doesn't necessarily have a place to live, and so you probably need some place to put those things as well. A lot of people just throw that all into the platform stack. So that's pretty much it. With all these changes, Jack is happy. He's making $1 trillion a year with his amazing Widgets Incorporated business. But Steve is in jail. He kept bugging us and he wouldn't leave us alone, so we had to call the police. Don't be Steve.